Hello everyone, I'm Yoshihiro Maruyama from the Australian National University. The title of my presentation is Categorical Artificial Intelligence, the Integration of Symbolic and Statistical AI for Verifiable, Ethical, and Trustworthy AI. So we propose the category theoretical integration of symbolic and statistical AI. Category theory emerged as a new structural foundation of mathematics as opposed to material set theory in the mid-20th century. It has recently been applied as a unifying modeling language for the sciences, including physics, computer science, AI, cognitive science, biology, and so forth. Categorical AI is a category theoretical approach to integrative AI. There is another related AGI talk by Tom Xu on categorical deep learning. Intended application area is science, AI, robotics. And there is yet another AGI talk by Michael Bennett on the three approaches to the artificial scientist. There is a debate between Peter Novick, Google's research director, and Noam Chomsky concerning the nature of intelligence. It's very much like the debate between empiricism versus rationalism in traditional philosophy, or like the debate between Bohr and Einstein on the nature of quantum theory. Novick and Bohr are basically empiricists. Chomsky and Einstein are basically rationalists. Chomsky, as a rationalist, argues that statistical language models have had engineering success, but that is irrelevant to science. Accurately modeling linguistic facts is just butterfly collecting. What matters in science, and specifically linguistics, is the underlying principles, which are like hidden variable theories in physics, which Einstein wanted to have, but refuted by what is called the Bell's theorem in Foundations of Quantum Theory. According to the Bell's theorem, there is no such local hidden variable theory. So basically, Einstein was wrong. I don't know whether Chomsky is ultimately wrong or correct. In contrast to this, Peter Novick argues that languages are complex, random, contingent biological processes that are subject to the whims of evolution and cultural change. What constitutes a language is not an eternal ideal form represented by the settings of a small number of parameters, but rather is a contingent outcome of complex processes. Since they are contingent, it seems they can only be analyzed with probabilistic models. So this is the Chomsky versus Novick debate. And the categorical integration of symbolic and statistical AI aims at reconciling Chomsky and Novick, unifying the two different paradigms of artificial intelligence, the symbolic and the statistical. And neurosymbolic AI in particular is a recent trend for the integration of symbolic and statistical AI, but it actually has an old origin in Marvin Minsky. Minsky argues that our purely numerical connectionist networks are inherently deficient in abilities to reason well. Our purely symbolic logical systems are inherently deficient in abilities to represent the all-important heuristic connections between things, the uncertain, approximate, and analogical linkages that we need for making new hypotheses. The versatility that we need can be found only in large-scale architectures that can exploit and manage the advantages of several types of representation at the same time. Then each can be used to overcome the deficiency of the others. Let me briefly explain what category theory is. In the early 20th century, set theory was foundations of mathematics based on substantivalism and the element-based worldview. Around the middle of the 20th century, category theory was born as some sort of functionalist foundations of mathematics, or it's based on the relation-based worldview. In this century, category theory has been applied as a unifying modeling language for the sciences, informatics, physics, AI, cognitive science, and so forth. Previously, it was foundations of mathematics, but these days, it's more like foundations of science in general. Category theory sheds light on structural interconnections between different fields of science, enabling interdisciplinary knowledge transfer. For example, there is categorical equivalence between logic, computation, and physics, as in this picture. The correspondence between logic and computer science is called Curry-Howard correspondence or Curry-Howard-Lambeck correspondence, including the category theory part. The correspondence between logic and physics is called the Abramsky-Cook correspondence. Conceptually, this means that the laws of reasons, logic is about the laws of reason, are structurally similar to the laws of nature. Physics is about the laws of nature. So in this sense, category theory allows us to go beyond the Cartesian dualism, which has separated the laws of reason from the laws of nature, or more generally, the laws of mind from the laws of nature. They have been separated by the Cartesian dualism. And yet, category theory allows us to reunify the laws of reason and the laws of nature. There are different sorts of categorical dualities across different sciences. Conceptually, the duality arises between the ontic and the epistemic. In logic, there is duality between formulae and their models. In algebraic geometry, there is duality between polynomials and their zeros. Like that, there are a variety of dualities in mathematics. Algebraic geometry, representation theory, Galois theory, topology, and I found duality in convex geometry between convex space and semantic domain, which is structure as used in the semantics of programming languages. In system science, there is duality between system and behavior. In program semantics, there is duality between states and observable properties, which is very similar to the duality in quantum physics between state space and algebra of observables. I found a duality in machine learning between kernels and reproducing kernel Hilbert spaces, in which kernels are regarded as two spaces of special form. I also applied the duality theory to knowledge representation and reasoning in artificial intelligence, which was published in Ichikai before. These dualities can be unified in terms of categorical theory of dualities, categorical general theory of dualities in such a way. So let me summarize the 4 objectives of categorical AI. The first objective is the structural integration of symbolic and statistical AI, which lays a foundation for the next generation paradigm of AI and for application below. The second objective is the ethical AI and AI for social good, which are enabled by correcting bottom-up machine biases in statistical AI with the top-down methods of symbolic AI. So the integrated AI contributes to ethical AI and AI for social good. The third objective is verifiable AI and AI for the logic of science in general, which are enabled by combining statistical AI for hypothesis discovery with symbolic AI for verification or justification. There is a picture for this in the next slide. The fourth objective is strengthening the unity and networking of science while keeping its plurality and diversity. It could be called pluralistic unified science, as enabled by category theory. Category theory arguably gives an integrative methodology to address the contemporary fragmentation of science. So this is a picture for the categorical integration of symbolic and statistical AI. Statistical AI works with inductive learning from empirical data, but it learns biases existing in dataset as shown by this well-known science paper. In terms of scientific inference, statistical AI is AI for the context of discovery. In contrast to this, symbolic AI works with deductive reasoning via logical principles and which can correct biases via top-down principles. And in terms of scientific inference, symbolic AI is AI for the context of justification. Combining them, we have the AI for both discovery and justification of hypotheses. That's the integrated AI. It's synthesis of discovery and justification in scientific inference. Integrated AI allows us to make empirical power compatible with rational understanding while correcting learned biases, machine-learned biases via top-down symbolic principles. Ethical principles expressed symbolically. Okay, so this is a picture for the integration of symbolic and statistical AI via category theory as a unifying framework. And more technically, we work on neural string diagrams as a universal symbolic language for categorical deep learning. Convolutional neural networks, transformer, and so on can all be formalized within this framework. This is an AGI paper with Tom Xu. Another thing is symbolic structure optimization via categorical compositionality principle, which is intended for applications to representation learning, latent space construction for chemical material design. This is joint work with Eli Sanish. And in natural language processing, we aim at something like categorical BERT for science AI applications, science NLP. Another thing I recently discussed at ICDL is emergence of symbolic compositionality in statistical transformer models. Okay, so that's all. Thank you for your attention.